So today, I'd like to talk with you about when to use Suvat in your A-level maths exam. So essentially, you use Suvat when you're trying to find an object that is under current constant acceleration, and for the five components like initial velocity, final velocity, acceleration, gravitational force, and time. If you happen to know three of these five things and you're trying to seek the fourth thing, then Suvat will be suitable. And here I've got a couple of examples to run you through today in order to demonstrate how an object undergoing constant acceleration can be used to find the fourth component or even the fifth component sometime if you use the Suvat equation. So let's get started. So here we have a picture of two particles, A and B, and it says that particle A has mass m kilograms and particle B has a mass of 3 kilograms, respectively. They are connected by a light inextendable string, and particle A is resting on this smooth plane here, this diagonal plane, at a 30-degree incline to the horizontal. The string passes through the pulley, the white bit here, this is the pulley, and is connected to particle B here. And it says that AP lies along the greater slope of the plane, and B is now hanging freely from the pulley, which you can see as well. Now, they release the system. At the moment, it's not moving, but the moment they release the system from rest means not moving, then B will drop by 0.25 meters, as you can see here, until it hits the ground. And of course, A will move up. So when you see questions like this, the first thing you should do is to redraw the diagram. Even though I know that the diagram here has been provided for you, it is important to redraw the diagram yourself in order to absorb the information. So let's do that. So on the space below here, I'm going to first redraw the slope and the ground, which is horizontal at 30%, 30 degree rather, on the incline. Here's particle A. Particle A has mg coming down. And because it's touching the surface of a plane, it will have a reaction force that is perpendicular to the point of contact. Hence, the reaction is here facing in the northwest direction. And here's the light inextendable string connected by the pulley. And here's particle B. Particle B weighs 3 kilograms, so we've got 3g pointing down. Opposing here is going to be tension. Tension will be pointing towards the pulley. There's no friction here because it says that the plane is actually smooth. Normally, if it's not a smooth surface, we would expect there to be friction opposing the direction of the movement. So here we don't need to add that. And one last information that we can add onto a diagram is the acceleration. As you can see in the question here, it says that after you release the system, particle B is accelerating at 2/5 g meters per second square. Now, because they are connected by a light inextendable string, and at the moment the string is taut, what that tells us is that A, at least until B hits the ground, will also have an acceleration that is 2/5 of g. Remember, as long as the string is taut, the acceleration will be constant throughout the two particles, and same goes for the tension. Okay, good. So we've listed all the information now. So let's work through the question here. So part A, it says find the tension in the string while B is descending. Well, okay, so if we take out, just isolate particle B as opposed to the entire system, and we use the equation F equals to ma, force equals mass times acceleration, the F here is the resultant force, which is the leading force minus the resistant force. M, obviously the mass of the particle, and A is acceleration. Well, what do we know here? Well, we can look at B. We know when we release the system that B is going to come down, not up. So that means that 3G is going to be the leading force, whilst the tension is going to be the resistant force. And hence, F here is going to be 3G minus T equals to MA. Well, we know M is 3. And A we also know, which is 2/5 of G. Okay, great. So now the T is the only thing unknown. What I can do is I can multiply the right-hand side. So this becomes 6/5 of G. I can bring the t to the right and 6/5 of g to the left. 3g minus 6/5 over g, well, that's just going to be 9 over 5g. And that's part A done. Okay, now to find m, so that's obviously finding the mass of A. So we can do the same thing exactly for particle A, also using F equals to ma. Now, slightly different this time, which is that for A, tension is actually the leading force as opposed to the resistant force. Because obviously when we release the system, A is going to move up the plane, and that's tension. So that's going to be the leading force. But what about the resistant force? What's going to drag particle A back? Well, there's no friction here. However, this angle is also 30 degrees. Why is that? Well, because if you look here, here's a right angle triangle where my cursor is moving. Here's a right angle triangle. If this is 90 degrees over here, then we know that this bit here has to be 60 degrees because a triangle, interior angles of a triangle add up to 180. So this is 60 and this is a right angle here. If this is 60, this one must be 30. So we can actually turn this mg away from the 30 degrees to make it come here. I'm going to draw this bit in red. If I do mg sine 30, so I would turn the mg force away from the 30, and this now becomes the resistant force. And now with the leading and the resistant force, I now have the resultant force. So I can write that out. So that's going to be T minus mg sine 30 equals to m, which we don't know, A we do know, which is 2/5 of g. Now, good news for us is that in part A, we've already worked out what tension is, which is 9/5 of g. Now, this is a generous question because they actually guide you using part A and part B to tell you that in order to work out M, you have to know T, the tension. In some exams, when they don't give you the split part where you have to do it on your own, then you're going to have to understand yourself that you have to find the tension first before actually finding the mass. But in this case, we're provided that. So let's just put that in. So that's going to not be 9/5 of G minus, well, sine 30 is just going to be a half. So that's just going to be half mg. And then I can multiply this. That's going to just be 2/5 mg. Now, notice here, all of the terms here, I got three terms and they all have a g. So I can just cancel all of them out because I can divide everything by g. And after that, I can move this to the right-hand side. So I have 9/5 is going to be 2/5 of m plus half m. So with some manipulation, right, turn this into a common denominator of 10. That's just going to give us 9/10 of m. Bring the 9/10 to the left-hand side by doing switch and flip. So we'll see that m is equals to 2. And that's your answer to part B. Okay, now, I know this topic is about Suvat. We haven't come to Suvat yet, but everything we've done is to gear us up in order to do the Suvat part, which is going to be in part C. So let's read on here. It says that the particle B strikes the ground and doesn't rebound. Find the time between the instant where B strikes the ground and the instant where A reaches the highest point on the plane. So what are they talking about here? Well, essentially what they're saying here is that when B drops by 0.25 meters, we know this to be 0.25 meters here as stated in the question. So B is going to come down here. So at this moment where B hits the ground, A is going to be somewhere up here, where it has also traveled 0.25 meters. But something differs between A and B. For B, because once it hits the ground, it just stays there. It tells us that it doesn't rebound. But for A, it doesn't just stay here. A is going to travel a little bit more before eventually coming to a rest. And so A is probably going to end up somewhere over here, where it finally comes to a stop. And that is what the question is talking about when they say the highest point on the plane. And we also know that it didn't hit the pulley over here because the question also stated that it doesn't actually hit the pulley when it comes to a stop. So we know that therefore B is going to come down here when we release the system. A is going to come up here when it hits the B, but then it's going to carry on traveling a little bit here and finishing over here. And our task is to find the time in between here when A is at this point where B hits the ground, and over here when it eventually comes to a stop. And with that, we can do Suvat. Okay, so let's do that. I'm going to scroll down to give ourselves a little bit more space. Sorry, that's the next question, which I'm going to just move on. Okay, let's do Suvat. Well, how do we do Suvat? Well, Suvat, first of all, you should always write the five components of Suvat. Displacement, S, initial velocity U, final velocity V, constant acceleration A, and time T. This is the five components of Suvat. And on this particular instance, we will first do the Suvat where it's at the beginning here, this blue A here, and the first time where B hits the ground, which is over here. Okay, we'll do the Suvat here first. So this is when the A is still ascending under the constant acceleration. So what do we know? Well, we know that it started from rest, so U is going to be 0. We know that V, well, actually, we don't know V. That's what we can find out. A, we know that that's going to be 2/5 of G. And displacement, well, we know it traveled 0.25 meters, so we can put 0.25 meters. Okay, so what equation do we know that has the component S, U, V, and A? Well, that's going to be V squared equals to U squared plus 2AS. Now we can put in numbers. So V squared is equals to 0 squared, which is 0, plus 2 times 2/5 of G times S, which is 0.25. Now, just to save us some time, if you just jumped ahead, if you put this in your calculator, square root it, you get V is equals to roughly 1.4 meters per second. So this tells us this is the final speed when B hits the ground and when A is over here. Okay. Now, the final speed of this point is actually the initial speed as well, when you go from here to here. The blue to the green, the final speed when you get here is actually the initial speed when you go from here to here, right? That's like a part 2 of this question. So now we're going to carry on. Now we know there's no more tension. And we're going to have to calculate the deceleration because we know we're slowing down, eventually coming to a rest from here to here. So how do we do that? Well, we just do F equals to ma again, but this time without the tension. So that's going to be minus mg sine 30. As we show in the diagram above, this is the resistant force. The resistant force will stay as it is. There's no more leading force. Equals to m. Well, we know what m is. M is 2. And this m here is also 2, so we can just cancel with this. And we know sine 30 is a half, so therefore the deceleration is going to be minus a half g. With this information, now we can go ahead and do Suvat one more time. Okay, so like I said, the initial velocity of part 2, where the string is now slack, is the same as the final velocity when the string is still taut. So that's 1.4. And we know V is going to be 0 because it eventually comes to an end. Acceleration we just worked out is minus a half g, negative meaning deceleration. And T is what we are trying to find. Well, what equation do we know that has the component U, V, A, and T under Suvat? Well, it has to be V equals to U plus AT. So let's put the numbers in. So that's going to be 0 equals 1.4 minus a half g times T. So I can bring the half gt to the left-hand side. That equals to 1.4. And of course, I can just bring this to the right. I can times this by 2 over g. And if you put that in your calculator, you get a fraction of 2/7. And there we go. So the time it took for the particle A to go from this point where B hits the ground to when it eventually comes to a halt, that's 2/7 seconds. And you see we've done Suvat here twice. The first time is assuming that it's still ascending with the tension still leading. And here is where there's no more tension. And that's our final answer here. And that's how it's done. Great. Okay, let's look at a second example, this time related to projectiles. Just move this down, give myself some space. Okay, so what do we have here? It says that a golf ball is driven from a point A with a speed of 40 meters per second and an angle of elevation of 30 degrees. And on the downward flight, it hits an advertising boarding at 15.1 meters above the level of A. Okay, so let's draw a diagram to represent that story. So here's the golf ball. Here's where point A is. This is where we hit the golf ball. And we started with, as I said, 40 meters per second. At an angle of elevation of 30 degrees. Okay, this is where we start. So the trajectory of the golf ball you would expect is going to go something like this. But then it says on its way down, it now hits a advertising board. So here's the advertising board here. Just write B for board. And they said that this is 15.1 meters above the level of A. So this is 15.1 meters. Okay, great. And that's essentially the story here. And the question I want us to find a couple of things. The time taken for the ball to reach the greatest height above A. Okay, well, let's start with that. So from this diagram, where is the greatest height above A? Well, it has to be here. This is the greatest height. Now, if you think about imagining you hitting a ball, a golf ball, or simply just throwing a ball upwards, what happens when the ball reaches the greatest height? Well, it actually stays stationary, albeit for a very, very short period of time. The ball actually stays still at the top of its trajectory. That's when it reaches its greatest height. Okay. Now, why is that useful? Why did I give that piece of information? Well, because if we were to do Suvat again, that's actually what V is going to be. So if we do Suvat now, we know that V has to be zero, no question about it, because we're trying to find the greatest height. Right? This is where the ball is stationary for temporarily, for a moment at least, up here. So that's equals to zero. What else do we know? Well, because when we do Suvat here, we are only doing the Suvat on the vertical component, right? Often the mistake student makes is they mix up the horizontal and the vertical component. We're doing Suvat here purely just imagining on a vertical component. So I'm not saying that at this point, greatest height, the golf ball has no speed whatsoever, but I'm just saying that purely from the vertical velocity component, it's zero because it's not rising anymore. Okay. Well, what about you? Well, this again, if you look at this 40 is the overall, velocity, which is a mixture of the vertical and the horizontal component. But I'm only interested in the vertical component here. So what I need to do is I need to resolve. I am only interested in the starting vertical velocity. Well, how do I do that? Well, just like in the previous question, what I can do is I can just resolve by turning the 40 away from the 30 degrees, which is a sine. So in fact, this is going to be 40 sine 30 meters per second. And that's my initial velocity. But what about acceleration? Well, again, just on a vertical component, we know that gravitational force act downwards, which is 9.8. But here, what have I done? Because I wrote this as positive, I have assumed that going upwards is positive. But gravitational force acts downwards. So therefore, I need to minus G on this side. Of course, I can switch them around. If you prefer, you want downwards to be positive, then simply make this G, but then this would have to be minus 40 sine 30. But you can't have it both ways. And the question asks for time, so time is what I'm trying to find. All right, so I have the component UVA, and I'm trying to find T. I have to use the equation V equals to U plus AT, exactly the same equation as above. So V is 0, U is 40 sine 30 minus G times T. Okay, so bring GT to the left-hand side. Here I got 40 sine 30. Well, sine 30 is a half, so just is going to be 20. So therefore T is just going to be 20 over G, which is roughly 2.04 if you put in your calculator to three significant figures. So that's how long it took for the golf ball to hit the greatest height over here. Great. Part B, the time taken from the ball to travel from A to B, right? So essentially over here. So we can do Suvat one more time, but we have to slightly change the numbers. Drag this all the way down. Okay, what do we know? Well, if you look at where we start, which is here, to where it hits the advertising board, we can see it's actually gone travel up by 15.1 meters overall. So that's going to be the displacement. So I'll put 15.1 over here. U, well, still the same. So 40 sine 30. Do I know the final velocity when it hits the advertising board? No, I don't. So I have to leave this blank for now. A is unchanged. That's going to be minus G. And I do know that T, well, I don't know T actually. I know that T, how long it took to get to the greatest height. So at best, I know as a sense check, it's going to be more than 2.04. And this is going to come in handy as you see in a second. Or I don't know what this is. I need to work that out. But what I do know is that this answer would have to be bigger than 2.04. Because if you look at the diagram here, it took the ball 2.04 seconds to even reach the greatest height. And we got to travel a little bit more before it hits the board. Okay, so now I have the component S, U, A, and T. Okay, so which equation should I use? That will be S equals to UT plus half AT squared. So let's put that in. 15.1 is equals to 40 sine 30. Well, we know 40 sine 30 is just going to be 20. So just put 20t minus half g t squared. Okay, now if I bring the 15.1 to the right-hand side and put the polynomial in descending order, that's going to be minus half gt squared plus 20t minus 15.1. So what we have here, as you can see, is a quadratic. And we know with quadratic equation that you're going to get two solutions. Okay, you can just put this in your calculator or you can do it manually. Either way is fine. If you were to do that, you get your answer t to be 1 and 3.08 to three significant figures. Now, which one is the right answer? Well, as I just said, that we know the answer would have to be greater than 2.04. So we know for sure that's going to be 3.08 and we can reject one. But the question is, why do we have one here then? Why do we have two answers? When does this happen? Well, if you look at the trajectory of the golf ball, it actually hits 15.1 meters twice. The first time is over here when it's on the up. When it's traveling towards its greatest height, it crosses 15.1 above point A once and then hit the greatest height and then come back down and hit it for the second time. So the t equals to 1 is actually for this one. It actually does reach 15.1 when 1 second after the golf ball is being hit, but that's not what we're interested in. We're interested in knowing when it hits the advertising board. So the second answer, 3.08, is what we want. So maybe on a separate question, the question might say, well, how long did the golf ball spend above the height of 15.1 meters? Well, then you can simply do the subtraction between these two, 3.08 minus 1, which is 2.08. That's not being asked for this question, but that could be for another day. And that's part B, right? Part B says, what is the time taken to go from A to B? Now, part C then. Part C says, what is the speed for which the ball hits the hoarding? Now, this is the wording here trips up a lot of students every year. They're looking for the speed, which is not velocity, right? So the speed is, if you do Pythagoras with the horizontal component of the velocity and the vertical component of the velocity, and you do Pythagoras, then you can work out the speed. Remember, speed doesn't have a direction, whereas a velocity does. Okay, so we need to do Pythagoras to turn it into the final speed. Okay, so therefore we need to know the uh, vertical component of the velocity and the horizontal component of the velocity when it hits the board. Well, let's start with the easy one, which is the vertical component. Essentially, what we're being asked to find is just this part here, v. So the numbers here don't change. So we can literally just use the same numbers we have, but we use a different equation. Perhaps let's say we use v equals to u plus 80. There are many choices, but let's just use v equals to u plus 80. So v is equals to u, again, 40 sine 30 is 20, plus a, which is minus g, times t, which we now know to be 3.08. So if you put this in your calculator, you get something like minus 10.2 to three significant figures, meters per second. Okay, this is only for the vertical component. So I'll put the v here, v of v, vertical component of the velocity. What about horizontal? Well, horizontal is actually much easier. If we come back up to the diagram here, what we're looking for is this component here in green. So that's when 40 turns towards 30 degrees. So this is actually 40 cos 30. And the good news is that this doesn't change. Right? We assume that the golf ball is traveling freely under resistance. So this 30 cos 30 for the horizontal component will not change at all. Okay. And 40 times cos 30, well, that's just going to be 20 root 3. So we've got our two components, right? This is the velocity for the horizontal component. So in order to find the speed, we can now do Pythagoras with the two numbers that we have. So the speed, that's going to be the square of the vertical component plus the square of the horizontal component square rooted. So if you put the numbers that we had just now, so that's going to be minus 10.2 square plus 20 root 3 square. Add them together, square root it, put in your calculator, you should get 36.1 meters per second to three significant figures. And that's it. That's going to be the speed for which the ball hits the boarding, and that's the final part as well. So as you can see, we've done two examples here, one on kinetic particles and one of them on projectiles. Both of them require us to do Suvat. That's because Suvat happens in more than one cases. So by practicing these type of questions, you should be able to be familiarized with when and how to use Suvat. The top tip is always use diagrams. Even if the diagram has been provided for you in the exam, draw it again anyway, because the words that they provided to you can be actually turned into additional information from the diagram that have missing information from the initial one that they provided for you. So always redraw the diagram to make sure that you took on every single piece of information written in the question. And that's how it's done. If you found this video to be useful, please give it a like and subscribe to our channel where we give tutees like you the insider knowledge that you need in order to get ahead at school and help you get the best grades possible. Together, we will help you thrive to reach your academic goals. And if you think anyone will benefit from this video, please share and subscribe, and also add any questions you have in the comment sections below. If you'd like to improve your chances of getting a good grade at A-level maths, and please don't hesitate to get in touch with me or our team of professionals. The contact information on your screen right now. I'm Dickson, one from the profs. Thank you for watching, and I wish you the very best of luck with your studies.